Welcome viewers to the second part of Advanced Tools and Techniques for Problem Solving and Decision Making. Here we will be dealing with LP formulation with graphical method. Coming to a product mix problem. Two or more products are usually produced using limited resources such as personnel, machines, raw materials, etc. And the profit that the firm seeks to maximize is based on the profit contribution per unit of each product. The company would like to determine how many units of each product it should produce so as to maximize overall profit given its limited resources. This is a maximization problem where the company wants to maximize its profit. A problem of this type is formulated in following example on the next slide. Mind it, in the previous lecture, in the previous part, we studied that three things are necessary for making an LP. That is objective function, alternatives, and constraints. So here we will also doing the same. We will be formulating all the three things. Coming to the furniture company data, there are hours required to produce one unit. A company is making tables and chairs. It has department of carpentry and painting and varnish. Carpentry department has total available hours per week equal to 240 and painting and varnishing have hours equal to 100 per week. Carpentry require a table 4 hours work while a chair requires 3 hours work for carpentry. Similarly, a table require 2 hours of painting and varnishing work while a chair requires 1 hour of painting and varnishing work. While going to the profit, a table while after it is made, it gives a profit of $7 while a chair gives a profit of $5. So this is a product mix problem. Now the problem is over here that how many tables and chairs should be made so that we can maximize our profit. So this is a linear programming model. How can we make this model? The mathematical formulation of the model is as profit amount is $7 for a table and $5 for a chair. The constraints will be 40 plus 3C must be less than 240 as the carpentry hours must be less than 240 hours and 4 into number of tables plus 3 into number of chairs because table required 4 hours and chair required 3 hours. So by combining these two, it must be less than 240 carpentry hours. Similarly, the same thing on paint and varnishing, 2T plus 1C less than equal to 100. And there are non-negative constraints, that is table and chair both should be greater than equal to 0 because they should not be less than equal to 0. They cannot be negative. And what is our objective function? It is 7 into T as the profit of a table is 7 and a profit of chair is 5. It is 7T plus 5C. We have to maximize this profit. So this is the LP problem. Now, how can we solve this problem? Coming to the graphical solution approach, let's say the easiest way to solve a small LP problem is with the graphical solution approach. Mind it, this is the easiest approach. The graphical method works only when there are two decision variables. This is basically the limitation of the graphical approach. It can deal with only two variables, but it provides valuable insight into how longer problems are structured. When there are more than two variables, it is not possible to plot the solution on the two-dimensional graph. A more complex approach is needed. Then we may use some tools, we may use some softwares for this, and we will be using those softwares, inshallah. Then, showing constraints on graph. For example, our first constraint was carpentry constraint, that is 4T plus 3C. If we find the extreme solution to the equations for t is equal to 0 on x-axis and y-axis, we find that the values are 0, 80, the coordinates are 0, 80 and 60, 0. we can plot these two coordinates on our lines, that is 0, 80 and 0, 80 on the y-axis line and 60, 0 on the x-axis line. Join the extreme points 60, 0 and 0, 80 by a straight line. We have joined it, and then after that we have made our carpentry constraint. So what's next? You know, this is the region which is bounded between between the axis and this constraint of carpentry. So this is basically the feasible region for carpentry constraints because it is less than equal to 240. So this is the feasible region which is bounded between these three lines. Now coming to the painting and varnishing constraints. Similarly, we have made two coordinates on y-axis and x-axis. On y-axis we have 0, 100 and on x-axis 50, 0. Similarly, we have plotted these two points 0, 100 and 50, 0. We join these points, and this is the painting and varnishing constraint. Again, the feasible region for painting constraints is plotted. So we have plotted these two feasible regions. Now we mix these two feasible regions with each other to find a common feasible region. How can we do that? Superimposing the two constraints. This was the carpentry constraint, this was the paint and varnishing constraint, and you know, this is the main feasible region which is the common between these two constraints. So this is the feasible region. Coming to the solution of it, we go with the corner point solution method. It involves looking at the profit at every corner point of the feasible region. The mathematical theory behind LP is that the optimal solution must lie at one of the corner points in the feasible region. So how we can do it with furniture company? You know that the feasible region for the Flair Furniture Company problem is a four-sided polygon with four corner or extreme points. These points are marked as 1, 2, 3 and 4. So these are four corner points. To find the T and C values means the coordinates producing the maximum profit, find the coordinates of each corner point and test their profit levels. We have done it like this, that for point 1 we have coordinate 0, 0 at origin. So for profit for it is with 7t plus 5c, which was our objective function, we have $0. So at point origin we have 0 profit. So it cannot be taken as maximum. Point 2, t is equal to 0, c is equal to 80. Means profit comes as 400, and for point 3, for T 30 and C 40, the profit comes $410. Similarly, for point 4, the profit comes $350. We have calculated the profit out of at these four corner points. So what is the maximum profit? This is the $410, which is basically the maximum profit. All right. Then what is the summary? How can we do it with corner point? If we make a summary, graph all constraints and find the feasible region. Find the corner points of the feasible region, compute the profit or cost at each of the feasible corner points, and select the corner point with the best value of the objective function found in step 3. This is the optimal solution. So this is basically the corner point solution with the help of a graphical method. Right. This is the end of my second part, and we will be meeting in the third part. Thank you very much.